Space is vast, yet collisions are commonplace. Gas and dust electrostatically flock together. Gravity takes over, coalescing grains into rocks, rocks into boulders, then asteroids colliding again and again, striking planets and each other. Stars collide, creating monsters of light and energy. Even galaxies collide over millions of years. Space is a rough place to be. That peaceful night sky cloaks a hidden danger. It might appear bejeweled, docile and permanent, but if you look closely you can see things happening, violent things. Stars engulfing planets and each other, protoplanets colliding, explosions rippling through gas clouds triggering the birth of young stars, black holes devouring everything in their path. Closer to home, a more immediate danger is the debris from the creation of our solar system, spinning about in a heliocentric orbit just waiting to bang into something like Earth. Collision avoidance is the name of the game, and we now have the technology to do something about it.
Catalina Sky Survey and other survey programs are really sort of the start of the whole planetary protection ecosystem. It starts with discovery, goes on to follow-up and characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover. In order to find a near-Earth asteroid, we take 4 images of a patch of sky separated by about 5 minutes.
And we take those 4 images and we blink them really fast, and it creates this little animation so we can see that the stars in the background are static, as they should be, and if there's anything that's moving, it'll pop out.
And our software compares those images and identifies things that are not moving, which are stars, and removes those, identifies things that are transient from frame to frame, and tries to link those up.
We've probably seen about 1 million asteroids in the last 7 years that the PANSARS has been operating. It's like picking a needle out of a haystack. We're looking for distinctive motion, and when we see distinctive motion in asteroids, we report them to the Minor Planet Center. The Minor Planet Center is the sort of world clearinghouse for near-Earth asteroids.
The Center for NEO Studies takes the observations from the Minor Planet Center and computes the high-precision orbits that we use to make predictions. CNEOS is also kind of an early warning system for newly discovered asteroids. We take the early data and we compute whether or not that asteroid could hit the Earth. If there's a chance, we'll send out an early warning and alert for follow-up observations so that we can get more data, and then we would know perhaps whether it can hit the Earth or not.
Asteroid impacts are a fact of life. The Earth has been impacted by asteroids continually through its history.
We saw in 2013 in Russia, a fairly small, by the standards of what we're finding, asteroid did hit the Earth. I feel a little bit like a guardian of the planet and doing my bit to try to protect people. It is a long-term process. It's going to take many, many years to find all of the dangerous asteroids.
The goal is to find near-Earth asteroids before they find us.
Having the right tools helps us look further away in greater detail. The Hubble Space Telescope was one such tool that was able to capture the first spectacular impact seen in our solar system. The Shoemaker-Levy 9 cometary fragments which struck Jupiter, leaving a surprising impression. Even more remarkable was the recent arrival of an interstellar object.
It was a special day when this object was first discovered. We have been waiting for the discovery of an interstellar object for decades, basically.
Well, when I first heard about this interstellar object, it was very exciting just from a scientific point of view that finally there's been an actual observation of such an object.
This object is simply a piece of another solar system that was expelled, and it has been traveling through interstellar space for hundreds of millions of years, billions of years, we don't know.
A number of our survey projects and other observatories immediately turned their telescopes to take observations of this object. From the observations we have so far, it looks like it's a very elongated object, maybe about a quarter mile in length.
We think this object, 2017 U1, is very long, perhaps 400 meters or so long, and very narrow, skinny, perhaps maybe 40 meters or so in the other dimensions. That's a very unusual shape. We don't see that in our solar system. None of the asteroids in our solar system look like that. So it's very puzzling how it could have obtained this shape.
We also see that it's very reddish in color, which indicates that it's been possibly in space a long time and irradiated by not only the light from our sun, but other suns as well.
Well, there's still quite a bit to learn about this interstellar object and limited time because it's on its way out of the solar system.
It's fading very fast. It's a relatively small object, so it's very dim. But we are continuing to try to use NASA assets like the Hubble Space Telescope and Spitzer to take observations to determine more about its size and composition.
NASA's Planetary Defense Coordination Office has a near-Earth object observations program which funds efforts that survey the skies to look for near-Earth asteroids and to calculate their orbits and their trajectories and to determine if any of them might pose a hazard to Earth. And as part of doing that, some amazing discoveries can happen, and the discovery of this interstellar object was one of them.
As our observational capabilities improve, Pan-STARRS has been getting better, other surveys have been getting better. There are new generation surveys that will come online. We will be detecting more of these in the future.
New observatories are being constructed. To be launched in the coming year, the James Webb Telescope will orbit at Earth's L2 Lagrange point 1.5 million miles from Earth away from the Sun. Its low-temperature sensors will be shielded from the Sun, Earth and Moon. There are also 3 new ground-based observatories underway. A multinational project being built in Hawaii, the 30-meter telescope, or TMT, will use 492 hexagonal elements, each about 1.44 meters, to construct the single primary mirror of 30 meters diameter. The secondary mirror will be 3.1 meters in diameter. The largest of all will be Europe's Extremely Large Telescope, or ELT. The primary mirror consists of 798 segments, each 1.4 meters wide, but only 50 millimeters thick, with a light collecting area of 978 square meters. The optical design calls for an immense secondary mirror, 4 meters in diameter, bigger than the primary mirrors of any of ESO's telescopes at La Silla. Then there is the giant Magellan telescope, currently under construction in the Chilean Andes, which will be ready by 2022. It consists of 7 8.4 meter diameter mirrors, making a total effective aperture of 24.5 meters. Housed in a rotating 22-story high building, it will produce images 10 times sharper than Hubble, with a total collection area of 368 square meters.
This is a project that we began in 2003. It was a small group of U.S. institutions and has now grown to an international project that includes Australia, Korea, Chile, and most recently Brazil. The next steps as we launch construction of this telescope are to build the mount, the steel mount that will hold the mirrors for the telescope, to build the enclosure, which is a 22-story building that has to rotate to allow you to move to different parts of the sky as you're looking out with the telescope.
It's a new epoch in the field of astronomy. It's a new epoch for cosmology, astrophysics, and the history of the universe. And so we'll be able to see things further and fainter than anyone has ever seen before.
And it just takes us to that next level of technical capability, and these technical leaps are what enable new discoveries.
The first 4 giant mirrors for Magellan have been manufactured. Number 5 is underway, as is construction at the site in the Chilean Andes.
GMT is really an exciting thing because we know that over the last 400 years that telescopes have gotten bigger, and that has allowed us to see things with better detail and to see fainter things and to figure out what the history of the universe has been. Our technology for doing this is getting better and better. We're able to build big mirrors, and we know how to do this. We know how to build GMT. We know how to build its individual mirrors and put them together. We know that when you build a telescope view, and the GMT will have a view that is 10 times sharper than the Hubble Space Telescope. And when you build a telescope that collects more light, and the GMT will collect 100 times as much light as the Hubble Space Telescope does, that you are going to be able to do things that we can imagine and set out as our goals, to look at the history of the universe, how things have changed, find out more about the dark energy and the dark matter. Those are things that we know you can do. But I think the really exciting things will be things that we haven't yet thought of, that the new questions that will come. The other part that's really interesting about a big telescope on the ground is that you can change it. That is, you can change the instrument. So I think that even when we build the telescope, that won't be its final form. Those instruments will eventually be replaced by better ones that use the technology that's developed over the period from now to then. We know that the universe has changed from a very homogeneous kind of goo at the time of the Big Bang into a highly differentiated world where there are planets, stars, galaxies, clusters of galaxies. The universe has gotten kind of interesting and complicated through the action of gravity over time. We'd like to see how that works. And by looking at what happened long ago, which means looking at very distant, very faint galaxies, and looking in detail, which means having the resolution to kind of really see what's going on.
No doubt revealing cosmic collisions far back in time and space. Not as close as the asteroid field, but still in our neighborhood, are other phenomena colliding in space. Out beyond the edge of our galaxy, the Milky Way is a cloud of hydrogen gas called Smith's Cloud, after its 1963 discoverer, Gale Smith. It is traveling at 312 kilometers per second, and is about to collide into the Perseus arm of our galaxy. Well, in 27 million years or so. It was believed to have been ejected from the Milky Way some 70 million years ago. Why is still not known, but when it collides with the galactic arm, it will trigger a brilliant burst of star formation with enough gas to produce over 2 million stars. Another major event to occur soon is in the heart of our galaxy, where a supermassive black hole resides. This black hole's mass is a hefty 4 million times that of the Sun. ESO telescopes have been tracking the motion of stars around the giant black hole for 20 years. Although huge, it is currently supplied with little material and is not shining brightly. But that is about to change. Recently, they have discovered a cloud of gas traveling towards the gravity sinkhole on a collision course.
The cloud consists mainly of hydrogen gas which we see anyhow in the galactic center all over the place. This particular cloud weighs more or less 3 times the mass of Earth, so it's a rather small and tiny blob only, but it glows very brightly in the light of the stars which are surrounding the cloud.
We really don't know where the cloud came from, but we do know that most of the material which is currently flowing into the galactic center black hole comes from stellar winds, material which is ejected by nearby stars. And could be that this particular cloud also was coming from a star ejecting material, but happened to produce a very compact and directed right at the black hole. Well, the next few years will be really fantastic and exciting because we are probing new territory. Here this cloud comes in, gets disrupted, but now it will begin to interact with the hot gas right around the black hole. We have never seen this before. We expect it gets hotter. It may even start emitting X-rays, very hard radiation, and then it gets disrupted, and then in the end we expect it to fall into the black hole once it's sort of going through all of this churning.
As the astronomers watched, the cloud has been picking up pace as it gets closer to the giant black hole. Its speed has doubled in the last 7 years, and it is now speeding towards the black hole at more than 8 million kilometers an hour. The astronomers have already seen the cloud's outer layers becoming more and more disrupted over the last few years as it approaches the black hole.
The black hole, imagine it sitting here, has a tremendous gravitational force, and the cloud, as it comes in, it will be elongated and stretched. It will become essentially like spaghetti. It will be elongated and falling into the black hole.
Observations of other massive black holes at the center of galaxies have revealed many varied phenomena. One galaxy's supermassive black hole is emitting a powerful outflow of material and, to the surprise of astronomers, is forming stars. Results from ESO's Very Large Telescope are the first confirmed observations of stars forming in this kind of extreme environment. The discovery has many consequences for understanding galaxy properties and evolution. Black holes at the centers of galaxies still hold many secrets. Galaxies are the building blocks of the universe. The giant galaxies we see today, even our own, were built up from many smaller galaxies, and construction isn't over. Today, full-grown galaxies approach and interact with each other. They may collide and eventually merge, growing larger and more influential. As the galaxies approach each other, the tug of gravity creates tides that distort their shapes. Stars and gas stream into new orbits. Sometimes they're completely ejected, trailing into the depths of intergalactic space. Clouds of gas are compressed in the chaos and ignite with intense rounds of new star formation. Computer simulations have been conducted and compared to actual images of galactic collisions, an uncanny resemblance. Because stars create most of the chemical elements, each galaxy has a particular chemical makeup. This makes identifying groups of stars from different galaxies easier. This infrared image of our sky shows our point of view of the Milky Way, 500 million stars. Most are in our galaxy, some belong to companion galaxies that orbit our Milky Way, and some are in between. Astronomers have discovered that some groups of stars belong to a different galaxy called the Sagittarius Dwarf Elliptical, and the Milky Way is cannibalizing it. As the dwarf galaxy passes through the Milky Way's disk, gravitational tides stretch the dwarf stars into long streams that wrap around the galaxy's orbit. For the dwarf, it's a fatal attraction. For the Milky Way, just another one of several similar events in its history. But something much bigger is headed our way. M31, the Andromeda Galaxy. This is the Milky Way's biggest neighbor, of roughly the same size, mass and type, and it is speeding towards us. Astronomers say the crash will begin in about 2 billion years. Supercomputer simulation shows how the event may unfold over billions of years. The first path distorts the two great spirals. Stars are tossed into the intergalactic night like sparks thrown from a campfire, and our sun, complete with planets in tow, could be similarly ejected. Gravity will eventually merge Andromeda and the Milky Way into a bigger single entity. With a new generation of telescopes looking skyward, we are sure to discover more dangers lurking in the heavens, though fortunately for us, they are millions or billions of years in time and distance away.